Hello, everybody. I'm Xiangbo Zhou. I'm working towards the PhD in University of Wollongong, Australia today. I'm going to talk about my recent progress, variable stiffness wires based on magnetorheological liquid metals. So I will share with you from 4 aspects. The first issue is the background introduction. It is widely used in the development of dampers and breakers and clutches and so on. Next, gallium and several of its alloys are liquid metals at or near room temperature, such as again. It has high electrical and thermal conductivity, large surface tension, and low toxic compared with mercury. And these properties make them attractive for realizing applications in flexible devices such as stretchable electronics, energy harvesting, and soft actuators. Recently, Ren et al. Has reported a liquid metal-based magnetoactive slurries, LMMS, formed by dispersing magneto-iron particles in a gallium-based LM matrix. The stiffness of the LMMS materials systems can be reversibly altered and subtly controlled within a short time and over a wide range. My research inspiration of this topic is derived from this. More research focus has been invested on using MRF to develop the devices with variable stiffness. However, there are relatively few studies that combine variable stiffness capability and good electrical conductivity at the same time. Here, a variable stiffness wire with high electrical conductivity is demonstrated based on LMMS. The wire consists of LMMS, a latex tube, 2 copper electrodes, and a fission line. The LMS is the core part of the wire, as it provides variety in stiffness and maintains the shape. It's formed by dispersing magnetic iron particles in gallium-based LM matrix with the help of condensed hydrochloric acid solution. This is a schematic illustrating the stiffness changing mechanism of variable stiffness wires. When we apply the magnetic field to the wires, iron particles in the LMS tend to be aligned along the direction of the applied magnetic field. As the appearance of rigid chains, the viscosity of LMS increases, and the required shear force is also increases. We adopt this principle to control the stiffness of the wire. We will get a stiffer wire with a stronger magnetic flux density. Next, we study the performance of the wires. As shown in the left panel, we connected the circuit through the thin copper electrode to light up the LED, and then stretch the wire. We can see the high flexibility. We also notice that in the whole process of the stretching, the brightness of the LED was almost unchanged, which slows the stable electrical conductivity. We further verify the tunable stiffness ability of the wire, as shown on the right, by comparing the presence and absence of a magnetic field. We can see its stiffness was significantly increased as the magnetic field was applied. And then we studied its conductivity and influencing factors. We measured one of the wires and focus found its conductivity is slightly higher than mercury, showing its good conductivity. Also, we tested the wire resistance under different stretching lengths and magnetic flux density. Although stretching will cause an increase in the resistance of the wire, the value was always being at a low level. The wire resistance changes slightly upon increasing the magnetic flux density. And the next section shows the influencing factors of its variable stiffness. We applied a laser to amplify the deformation as shown in the left. And when we increase the magnetic flux density or the mass content of iron, we found the wire stiffness is enhanced. We further explore the influence of the radial magnetic field on the axial deformation of the wire, as shown on the right. We observe that increasing the intensity of the magnetic field not only slows down the stretching speed, but also reduces the amount of deformation. After examining the parameters affecting the variable stiffness performance, we investigate the application of wires in the field of stretchable electronics and soft robotics. This picture shows the wire ability of shape maintaining. We use the wire in front of electromagnet to display the shape of USTC. And this picture shows the switch controlling ability. The wire was pressed and rubbed by hand to disconnect the circuit and released to connect. A pressure of about 160 million pascals is needed to bring the current to almost zero. We designed a soft gripper driven by an electromagnet, and this is a video of soft gripper. We placed two wires side by side directly below the electromagnet as the contact part of the gripper. The gripper based on the wire can be used to grip objects of various shapes. Combining the variable stiffness and conductive properties of wires, a self-propelled variable stiffness wire was proposed. The wire is connected in series with the coil. The wire stiffness can be controlled by directly controlling the current passed through it. In order to increase the variable stiffness range of the wire, we explore the use of gallium to replace EIS alloy for improving the stiffness of the wire at room temperature. The gallium-based LMS wire can change its stiffness by two ways: liquid-solid phase transition and magnetorheological effect. At room temperature, the solid-state gallium LMS behaved like gallium. The wire was rigid. In the stretching experiment, as the ratio increased from 1.5 to 5, the ultimate tensile stress increased from about 10 to 20 million pascals. When compressing, it shows the Young's module was increased from 400 million pascal to about 700 million pascal. We maintain the temperature at about 50 degrees Celsius using a contactless induction heater throughout the process to ensure the wires were at liquid state, and its compression performance is similar to that of the wire made of EIS alloy in a relatively low stage. Employing the fluidic nature of gallium and liquid solid phase transition, we also explore the self-healing ability of the gallium-based wire. Heating the wire to about 50 degrees Celsius, LMS melted into liquid state and could smoothly flow and merge to heat the circuit due to the fluidity of liquid metal. We first connected the gallium-based wire to the circuit to light up a LED. And after it breaking, we heated to 40 degrees Celsius and could smoothly make the LMS flow and heal the circuit and reconnect it. In summary, this work presented a reversibly variable stiffness wires based on liquid metal rheological slurries. It has good flexibility, high electrical conductivity, and the ability to change its stiffness upon the application of stimuli. And it possessed multiple applications. What's more, we are working on solving the problems of the LMS continuously generating a small amount of gas and slow down the sedimentation and aggregation of iron particles in again. And thank you very much for your attention.